Hi, I'm Hamish,
And I'm Max.
and this is ChessYP. It's our robotic chess training partner. It uses computer vision to detect our moves and an electromagnet on an XY plotter to respond. The system is fully integrated onto a Raspberry Pi, and it works inside an intuitive touchscreen interface.
But before we dive into the finer details of its design, it's important to know why we built it in the first place.
Modern day chess is played largely online, either on a computer or on a handheld device. There are clear advantages to this format. You can always find a game with someone at your skill level, and you can also access a wealth of training information.
Yet, chess at its heart is a board game. Those who prefer to play over the board or would like to practice for an upcoming in-person tournament against a strong opponent have no practical means of doing so. Phone screens are small and impractical, and computers do not adequately simulate physical play either. Besides, nobody wants to spend all their time hunched over a phone screen.
Practicing in person is also difficult for those who are unable to find a suitable training partner at higher skill levels. Chess training books are a good start, but they won't be able to simulate playing a full game to its completion over the board.
With these issues in mind, the aim of this project was to successfully integrate three elements of chess playing into our robot: detecting moves, computing a response, and physically moving a piece to the desired square. These elements should be implemented to the successful completion of an entire game.
So overall, this was an exercise both in creating something and in project management. We worked with a limited budget and time span, as well as with the added responsibilities of creating a final report, a poster, and of course, this video.
With our problem to solve and our project aim determined, let's take a closer look at what we built.
ChessYP's physical structure consists of two square acrylic pieces, a base and a top, which are screwed together by 12 pillars distributed around the border of the base. Both platforms are made from a 65 by 65 centimeter square of plexiglass acrylic, which is 60 millimeters thick.
These dimensions were arrived at after carefully considering the concave bending in the acrylic. As shown here, the top concaves at the center of the platform, and the electromagnet height has been appropriately adjusted to account for the change in verticality.
An XY plotter operates at the base of the structure, made from a 20mm V-slot aluminium railing, which features a V-shaped extrusion on each face to hold the wheels on a total of 3 gantries. A timing belt loops around 2 stepper motors and is neatly tied to the 4 corners of the main gantry. Some parts, such as these platforms for the stepper motors, needed to be 3D printed. The 2 stepper motors can coordinate the electromagnet anywhere within this area of operation, using a combination of clockwise and anti-clockwise motion. This arrangement is more complex than the H-bolt, which only uses 1 motor per dimension, but it maximizes our envelope of operation.
Limit switches attached to the railings of the XY plotter ensure that we can calibrate the position of the electromagnet throughout the game by triggering GPIO pins on the Raspberry Pi.
The electromagnet is wrapped in a piece of cotton material that protects the acrylic from scratches. Despite the appearance of a kidnapping, the electromagnet is unharmed and the board still looks clean from scratches after weeks of testing.
Our screen display is detachable from the rest of the machine, so that players can either interact with a touchscreen setup shown here or an external monitor, with the aid of a mouse and keyboard. This was a deliberate design choice to allow for the most flexible and user-friendly experience.
The game is played on a matte sticker chessboard. At this project's proposal, we'd envisioned a laser-cut board onto the underside of this acrylic, similar to the board shown here. Unfortunately, reflections on the top of the plexiglass and the cabling moving underneath the plexiglass rendered computer vision practically impossible with this solution. The sticker shown here ensures that no reflections are visible on the opaque board and the cable isn't visible underneath, so the camera can see the board state on top.
Outlining the board are chess pieces which have been laser cut into the underside of the acrylic. This is called the graveyard, where captured pieces are returned to.
A crucial consideration for our project was the size of each square, as our chess pieces, which are 3D printed, are designed with neodymium magnets implanted at their base. They must be positioned close enough to one another to have a practical game of chess, yet not too close that the electromagnet can accidentally interfere with unintended pieces during movement.
The system operates on a Raspberry Pi, which coordinates the stepper motors, electromagnet, and attached camera. The system is run on Python using functions prompted by user inputs on the GUI. Libraries like tkinter construct the user interface, and a universal chess interface and Stockfish are run simultaneously to our code to create a language that can perform logic on chess board states.
A breadboard is glued underneath the base platform, below the XY plotter's envelope of operation, to house ChessYP's circuitry. This can be covered up by simple housing for aesthetics, but was preferred over a PCB to enable modification and replacement of components if there were any issues over the life of the project.
The electromagnet is powered by an independent 12-volt DC supply triggered by a GPIO pin, and the motors are driven by A4988 stepper motor driver chips that interface to 4 pins on the Pi that can adjust direction and input steps, and a decoupling capacitor was added to protect the drivers after blowing one up in early testing.
In terms of software design, our graphical user interface is a good place to start with explaining how ChessYP's software works. Simple buttons and sliders allow the user to input moves, adjust the difficulty, undo moves, begin new moves, and see the chess computer evaluate positions.
At the start of the game, we use edge detection functions contained in OpenCV to seek out the corners of the chessboard. Once the internal corners of the chessboard are known, we use trigonometry to determine which internal corner is closest to the edge of the image, then warp the outermost corners to the known pixel values that align with a 2D board representation. This process means we can warp any 3D image of a chessboard onto a 2D plane. The transformation matrix is then saved and used for the remainder of the game unless the camera is recalibrated. One limitation of this approach is that the camera cannot be moved around the room throughout the game, but the user can refer to a camera feed of the 2D board to see any misalignment.
The warped images are then segmented into 64 squares, representing the chessboard. Once the board is recognized and calibrated, move detection uses an image difference function to calculate the change in pixel brightness values from one image before and one image after a move is made. The buttons Begin Move and Submit Move on the GUI are used to take pictures at these 2 critical moments. This example shows a basic move, E2, E4, being detected by the robot.
We can then sum the total brightness difference across each square and create an ordered list of which chess squares change the most. We can then test different orders of pairs, from most likely to least likely, against a list of legal moves in the given position. These legal moves are calculated using the current game state, which was handled by a universal chess interface running simultaneously to our script. However, this approach is not always applicable. Not every move in chess leaves only 2 squares altered. Castling and en passant, for example, result in changes on 4 or 3 squares respectively, and thus separate functions were written for these cases.
We also have an overwrite prediction function, which allows users to correct the predicted move and update the robot's perceived state of the board if there was an incorrect move detected.
Once a move is correctly detected, it's time for ChessYP to respond. Using Stockfish 15, a superhuman chess algorithm, a response move is determined according to the difficulty level set by the sliders on the GUI. The coordinates of the source and destination squares are fed into a path planning algorithm to determine one of 3 modes of transit that the piece should take.
Firstly, pieces can move in either horizontal, vertical, or diagonal lines. Fortunately, legal moves of most pieces follow unobstructed paths in these cases.
Second, knight moves and castling are examples where one piece must move around another by going along the edge of 2 squares.
Finally, the robot must send captured pieces to the graveyard. In this case, the pathing algorithm avoids all obstacles as the piece is moved outside the board. After the robot has responded, the board state is updated and the game continues, move after move, until its completion. At any position, the user can run a deep evaluation to obtain a precise evaluation of the game, approximately how many points they are winning or losing by. Additionally, if stuck in a tricky situation, the user can also opt for the best move in a position to see if there's a clever way out.
We hope you've enjoyed this introduction to ChessYP. There are some areas of future work that can further improve its functionality.
Firstly, we could replace the breadboard with a printed circuit board, which could provide for a more professional looking aesthetic.
Second, we can improve the look of the board by replacing the sticker with an opaque laser cut similar to our project proposal, but with colored squares to ensure opacity. Pathing to the graveyard could also be optimized further, as well as adjusting the speed during pathing certain moves which currently look visually jarring.
Finally, adding some training functionality, such as the implementation of puzzles or set positions from previous games, would help players get the most out of their training sessions.
Thanks for watching.
Thank you.
All right.
Cut.